It's a great start.
Great start. Okay. Welcome back to another episode of the No Lift podcast with myself, Arthur Lynch. And we're back with another paper discussion in this episode, which is brilliant because it's an opportunity to welcome back Ian Dara onto the show. Ian, how are you?
Not too bad, Arthur. How are you?
Doing well, man. On brand, as you can see, the No Lift hat and t-shirt.
You're gonna have to make these available for sale again. I'd buy a good tank top.
Yeah, I'm just woefully disorganized, and whenever I start at that kind of carry on, it just gets very messy, and I just know I'm providing a terrible service. So better provide no service than a bad one. That's what I say. Jokes aside, though, if you're looking for t-shirts, hats, sweatshirts, Christmas time just around the corner, it's an ideal present.
If they were available.
If available, yeah. Okay, so the paper we're going to discuss is titled Extraordinary Fast Twitch Fiber Abundance in Elite Weightlifters. It's by Serrano and colleagues, published in 2019. And this is one that you brought to my attention. Is there a spiel you want to give before we get into it, or will I just get straight into the abstract?
Yeah, well, brought to your attention is maybe a soft way of putting it. I think I badgered you into doing this paper review with me, that every time you're like, what paper do you want to do? I'm like, this one. Yeah, maybe. What about now? Yeah, well, this is a paper that's this is one of the terrible things you unfortunately end up saying when you pursue a career in research, is that this is one of my pet favorite papers, and that I kind of come back to it semi-regularly just because it combines a professional interest of mine, which is muscle fiber typology, which is kind of just the study of like muscle fiber types and also the profiling of muscle fiber types in organisms, and then obviously Olympic weightlifting, which is my kind of hobby of choice, I suppose. So yeah, thanks for finally agreeing to discuss this paper with me, though I don't know if it keeps in line with our ambition to be discussing current research, because this paper is nearly 3 years old now, but still we'll get through it.
I mean, it doesn't have an expiration date. I'm sure if you were to do the same study again now, the results wouldn't differ that much.
We hope. Yeah,
we hope. Yeah. And 2019, it's not that long ago, really. It feels it because of the pandemic, but it's not.
Yeah, that's actually just, it was about a year before COVID, so peak before times. Yeah.
Cool. So I'll read the abstract for the benefit of the audio only listeners, and then we'll dissect it as we see fit. Okay.
Yeah, perfect.
So the abstract: human skeletal muscle fibers exist across a continuum of slow to fast twitch. The amount of each fiber type influences muscle performance, but remains largely unexplored in elite athletes, particularly from strength or power sports. To address this nescience, that was a new word for me, fastest lateralis biopsies were performed on world/Olympic and national caliber American weightlifters. Participant accolades included 3 Olympic Games, 19 World Championships, 25 national records, and over 170 national or international medals. Samples were analyzed for myosin heavy chain content via SDS page using 2 distinct techniques: the single fiber distribution percentage and homogeneous composition. The main finding was that these athletes displayed the highest pure MHC2A concentrations ever reported in healthy vastus lateralis. So 23.9% type 1, 5% type 1, type 2A hybrid, 67% type 2A, and 6% type 2A, type 2X hybrid. With world caliber females expressing a notable 71% type 2A. Yeah, no pure MHC2X were found with the single fiber technique. Secondary analysis revealed the heavyweights accounted for 91% of the MHC2A, 2X hybrid fibers, which cause a correlation between this fiber type and body mass. Additionally, when compared with single fiber technique, homogeneous composition overestimated MHC type 1 and type 2X by misclassifying type 1, type 2A hybrid fibers and type 1 and type 2A, type 2X hybrid fibers as type 2X, highlighting the limitation of the homogeneous composition technique as a measure of isoform distribution. These results collectively suggest that athlete caliber, world versus national, and our years competing in the sport determine fiber type percentage more than sex, particularly for MHC2A. The extreme fast twitch myofiber abundance likely explains how elite weightlifters generate high forces in rapid timeframes. So there's a lot in that.
Yeah, and it's maybe probably worth, before we go on, it's probably worth putting into English some of the things that are kind of mentioned there. So for example, if anybody's listening and heard the words MHC type 2A X hybrid fiber and went, what on earth does that possibly mean? It's probably worth just explaining what those are supposed to be, because they're essentially they're indices of fiber type. And then maybe it's probably also worth mentioning what the concept of a hybrid muscle fiber is as well. So I think most people are familiar with the idea, even if they don't really understand what the physiology is, of the idea of like a fast twitch and a slow twitch muscle fiber. And that term actually is derived from, believe it or not, this is one of my favorite things to say, that there is a discipline called molecular biomechanics, where they essentially look at either molecular or cellular interactions and try to do things like measure the force of an individual muscle fiber contraction and stuff like that, which is, I don't know, if you're into that sort of thing, it's mind-boggling to think that people do those kind of experiments. But either way, the term fast twitch and slow twitch actually come from the time it takes certain kind of subpopulations of muscle fibers to reach peak tension. So if I take a muscle fiber, I extract it and I stimulate it to contract, the amount of time it takes a given fiber to reach peak tension will vary between subtypes of fibers, and then they can be classified as fast twitch or slow twitch based off that. So obviously fast twitch fibers reach peak tension faster, slow twitch slower. And then within the fast twitch population, there's kind of, traditionally speaking, there's two subpopulations. So you have what's called the type 2A fast twitch fiber. So type 1 is slow twitch, type 2 is fast twitch. And then you have the type 2X subpopulation of muscle fibers. Kind of speaking in, again, this is probably considered more traditional terms now, because one of the things we'll talk about is how it's not really a discrete scenario. So it's not really, there are three discrete fiber types. It's more of a continuum, which is alluded in the abstract here. Type 2X traditionally are the fastest twitch, so they'll reach peak tension the quickest. Type 2A are kind of sometimes referred to as like intermediate fibers, so they are a fast twitch fiber, but they do not reach peak tension as quickly as the type 2X fiber, but are quicker than a type 1 fiber. There's also an association with fatigability here as well. So type 2 fibers are generally considered to fatigue much quicker than type 1 fibers, with type 2X fatiguing the fastest, type 2A fatiguing kind of somewhere in the middle, and type 1 being the most fatigue resistant. Why that's important to sporting events, obviously, then is you can kind of look at the demands of a sporting event and then associate that with a greater abundance of a certain fiber type being advantageous to performance. So what I mean there is, if I'm running a marathon and say I'm a super elite marathon runner, so I'm running a marathon in 2 hours and some change, it makes sense that I want my muscle to be mostly composed of muscle fibers that are very able to resist fatigue. Hence, you say endurance athletes are type 1 dominant. So what we're looking at in this paper today then is, type 2 fibers and an event, Olympic weightlifting, which is very low time demand. A snatch takes whatever 1 to 2 seconds, a clean and jerk slightly longer than that, if even, but a very high force demand, because the objective is to lift the greatest amount of weight. Therefore, type 2 fibers would be expectable to be advantageous. The idea of the hybrid fiber then is just something I'll comment on briefly before we actually dig into the paper itself. And this is something that was kind of uncovered, I think, initially using cross-sectional analysis of muscle fibers, but now it's this single fiber analysis technique which is used during this paper, which is the kind of gold standard method for identifying hybrid fibers. And a hybrid fiber is essentially a muscle fiber that expresses markers that are indicators of a single fiber type. And MHC, which stands for myosin heavy chain, is actually probably the most popular marker used to identify muscle fibers. So myosin heavy chain, myosin is a cytoskeletal protein. So it's a protein that's involved in making up the skeleton of a cell. They're usually involved in intracellular transport, and they're involved in muscle contraction as well. So myosin heavy chain, if anyone's done a very basic muscle physiology course and heard of like cross bridge cycling and muscle contraction, myosin heavy chain is that kind of golf club shaped protein that essentially pivots when a muscle contracts and causes a sarcomere to shorten. There's different versions of myosin heavy chain, and these are expressed in different muscle fiber types. So MHC1, myosin heavy chain 1, is expressed, traditionally speaking, exclusively in type 1 muscle fibers. MHC2A is expressed in type 2A muscle fibers, and MHC2X is expressed in type 2X muscle fibers. So the idea being that if I take a muscle fiber and I detect MHC1, I can say, oh, that's a type 1 muscle fiber. However, when single fiber analysis and other techniques started to be performed, it was discovered that there are fibers that will co-express MHC proteins. And these are the so-called hybrid fibers. So you'll have a muscle fiber that you'll be able to detect both MHC2A and MHC2X, or MHC2A and MHC1. Now, to my knowledge, it's not entirely clear if I wouldn't describe them as distinct fiber subpopulations, because one of the things you see with exercise training is like a transition of hybrid fibers. So someone who's untrained might have a higher abundance of 2A, 2X fibers. They go away and do some training, and they have more 2A fibers and lower 2A, 2X hybrids. So there is an idea that these are maybe a transitory state. So essentially, these are fibers that are turning from one subpopulation to another. But it's also unclear if they have distinct functional properties. So does a type 2A, type 2X fiber behave more like a type 2X fiber or a type 2A fiber? This we don't know. It's probably, again, on a continuum. It'll depend. If it's a transition, it'll depend on how close that fiber is to its complete transition state. And I'm using parentheses there, between 2A and 2X. So that's essentially what is meant by the fiber types, and what that MHC protein, it's simply a marker of a fiber type, and what's meant by a hybrid fiber as well. So that's worth explaining, because we're going to encounter that when we look at the results from this study. We should probably talk about what they actually did in the study first, like how they collected the data, because that's interesting too. I don't know if you know, right, how the study was performed.
Well, we'll get to that in a moment. But I think just going through the intro to give a little bit more context for people. So like, this is kind of what we know about muscle fiber types in strength and power athletes. And they've kind of highlighted the type 2A, and there's this sort of abundance of type 2A fiber types in various different strength and power athletes across different, levels of performance. But I'm also going to highlight the type 2X mainly because of how low it is. And that's,
Yeah.
like we were saying off air beforehand, you know, if you hadn't encountered much of this literature before, you might assume that these type of athletes would have a very high proportion of type 2X. So maybe you want to comment on why we don't see that.
Yeah. So this is actually something you see thrown around a lot. So I particularly see it on, and I don't mean this actually as a criticism to people, but you do see a lot of like, and people will say to me, you know, you might watch Usain Bolt sprinting or Ilya Lin snatching or something. They go, he's all type 2X, all type 2X. Or you'll see it in physiology classrooms where there'll be kind of, you'll see a picture of a guy sprinting and you're like, this guy will, you know, everyone in the class comment, what fiber type do you think this athlete is, you know, and everyone will say type 2X. But yeah, when it comes to actual measurement of when you do muscle fiber typing, you tend to not necessarily see a high amount of type 2X fibers in anybody. And what they're highlighting here is, in fact, in athletes where it's theoretically it's not an, you know, it's not a bad idea to think that maybe these athletes would mostly have type 2X muscle fibers. You do in fact see type 2A. There's kind of a couple of lines of thought as to why there's kind of this this shift to a type 2A phenotype over a type 2X one in power and explosive athletes. The first is to do with muscle recruitment. So essentially there's this thing called the size principle, and essentially muscle fibers are recruited when you send a signal to the muscle. So a muscle is stimulated to contract by essentially an electrical signal. So a signal from the central nervous system, from the brain, tells a muscle to contract. And basically different muscle fibers will have different recruitment thresholds. And generally the recruitment thresholds, the lowest is in type 1 fibers, kind of let's say the middle is in type 2A fibers, and then the highest is in type 2X fibers. So what that means is you really need to send an extremely strong signal to a given muscle, because one of the things you have to realize as well is these muscle fibers in a muscle, there may be kind of some degree of regional distribution, but they're not in separate compartments. So you don't have a part of your leg that is all type 2 muscle fibers and a part of your leg that is all type 1 muscle fibers. Generally, if you extract a muscle sample, you're going to have kind of a hodgepodge of 1 and 2 type 2 muscle fibers. So essentially, one of the reasons why it's suspected that there is a lower abundance of type 2X fibers is maybe they take too much stimulus to recruit. So you're actually better off recruiting more type 2A muscle fibers because you can recruit more of them with less of a stimulus than type 2X muscle fibers. And that's why there's this kind of favoring of this with strength and power athletes. Another is perhaps to do with the fatigability. So simply because they fatigue the fastest, even though they may be the greatest abundance, they may have the kind of greatest time to peak tension, they fatigue too quickly, perhaps even for very high force output events like throwing a shot put or snatching or something like that. Even though, speaking kind of a little bit out of step and to go on a tangent here, evolutionarily, considering the way humans function in nature, you wouldn't want a high abundance of type 2X muscle fibers because they fatigue so fast. And they're even kind of poorer at things like substrate utilization. So oxidizing glucose, oxidizing fat, they have the lowest mitochondrial density. Like humans are kind of animals of persistence, you know, like we're one of the best long duration endurance. We are the best long duration endurance mammal on the planet. And so for us to have a high abundance of, you know, very fatigable, difficult to recruit muscle fibers, it would be kind of, it would go against the way we've performed in nature. So it's potentially that they've been selected against as well, evolutionarily. I don't know, I'm speculating there. But that's why. So the reality of why you would see maybe more type 2A muscle fibers in these athletes is they are still, they're still fast twitch, they're still able to produce a high amount of force, but they're easier to recruit and they're perhaps not as fatigable as well. So that's possibly why.
Very good. So now I will let you talk about what they did in the study here. So we'll move on to the methods here, because I don't think there's anything more we need to talk about in the intro.
No, definitely not. And actually, like I guess there's it's really impressive what they did. So the 2017 World Weightlifting Championships were hosted in somewhere in California. It's actually escaping me. Where I want to say Anaheim, but I don't even know if Anaheim is in California. So I'm not entirely confident about that. But it was somewhere in California, and essentially what these guys did, and also USA Weightlifting ran the American Open. It was either directly before or directly after the World Weightlifting Championships. So they did the AO finals for that year. Basically, they had a super competition essentially. And what they did is they put an ad out, and they basically offered to shuttle bus athletes after they had competed to the lab to give a muscle biopsy sample. So it was pretty impressive. I have to commend them for kind of maybe saying the balls of like let's try and do this. And by doing so, they happened to recruit a cohort of 21 weightlifters here. Now they didn't seem to get any male competitors from the World Weightlifting Championships, only females, but they got a few people from, excuse me, from the AO finals as well. So I think their criteria for the international elite weightlifters were they had competed either in the previous World Championships or Pan American Games. And for the national level weightlifters, they placed top 5 in the AO finals, which is like America for and again, I'll use parentheses here, for drug-free weightlifting are pretty good. And when you look at the totals that were, or the relative snatch and clean and jerks that were reported by these athletes, they're pretty decent. So this is, I would say, this is a decent cohort of high-level weightlifters, which is impressive because these athletes are very hard to recruit, and particularly to get them to give muscle is challenging. So that's what they did. The athletes were shuttled to the lab, gave a muscle biopsy, and reported their total. I think that's basically all the athletes were asked to do.
Yeah, and I'd also like to emphasize that point about how impressive it was to get that kind of a sample and the context around when it was performed as well. Like I can only imagine, for example, so between 2 and 96 hours after competing, if someone even gave me a survey at that point, I would be like, would you go away? So to volunteer for a biopsy study is no mean feat. So I have to speculate that the researchers have some fairly powerful powers of persuasion in order to recruit those and convince those subjects to participate.
I don't actually remember, because I give the bus anecdote because I vaguely remember seeing a tweet or an Instagram post from Andy Galpin, who's the principal investigator on this paper, just being like, we'll bus you, come to our, please participate in our study. I don't actually remember if they offered an incentive or not in terms of, hey, we'll give you $50 or $100, which is, just for listeners, that's to me, that's not something that's unethical or something like that. That does happen in studies, particularly studies with invasive procedures like muscle biopsy. So there's nothing wrong with that, in my opinion. I just don't remember if they did it or not. Probably something to comment on, I think it's at the bottom of the participant section, is one of the athletes, and I think they were included in the analysis, got popped after this. I actually don't know who it was, and obviously we wouldn't comment if we did know who it was. Although it would have been nice, I guess you couldn't do it because it's easier to find out who the individual was. It would be nice to know which athlete that was if it was just flagged or something like that, because Andy actually has another study on what's his name, Mark Bell's. They did a muscle biopsy on Mark Bell, who is obviously from what I understand, if he wasn't a heavy drug user, performance enhancing drug user for some time, he's definitely a consistent performance enhancing drug user. So there would be effects on probably muscle fiber typology from extended and heavy periods of performance enhancing drug use. So it would have been nice to know not necessarily who that person was, but which participant that was, or having that flagged in some way. But I mean, it's only one person. that's not to say any of these other athletes may not have been taking drugs or not, but only one of them was popped anyway. But yeah, still, I read that, and it does give you a bit of a smirk to see things like that.
I had a wee chuckle at it as well, I must say. Yeah, like, do with that what you will.
Look, that's weightlifting. Unfortunately, that's the nature of the sport.
Of course,
you know, those who know, but it's not exactly as surprising that would have been reported in this study, you know, or and it's to be fair, it's transparent of them, which you have to respect. But I think many people who would read this study and would know would have some degree of expectation of something like that towards at least some of the athletes in this cohort. It's unfortunate, but it's the way the sport is.
Sure. So on the biopsy technique then, so following 30 minutes of supine rests, athletes underwent a mid-muscle belly, so approximately halfway between the greater trochanter and the patella, biopsy of the vastus lateralis. Some listeners may or may not be interested to know about why there's this focus on the vastus lateralis in studies where there's a biopsy taken. My understanding is twofold, in that, so I mean, you've obviously your four quad muscles, your vastus lateralis, your rectus femoris, your vastus intermedius, and your vastus medialis. There is a risk that if you were to take it on the medial side, that you could nick the femoral artery. And then obviously the vastus intermedius is a deep muscle, so it's not as easy to, I don't know if you could biopsy it. And then with the rectus femoris, there's a little bit too much going on there because it's a biarticulate muscle that crosses the hip joint as well. So that's my understanding of why the vastus lateralis is typically where the biopsy is taken from. Do you have anything to add to that, or?
Yeah, my understanding is the same, that it's twofold. The first is convenience. So for listeners who are not up to date on their anatomy, if you want to know where your vastus lateralis is, I would say put your hand on the outside of your knee and essentially just pull your hand halfway up your thigh, and that is approximately where they would have taken this muscle biopsy. So your vastus lateralis lateral is the quadricep muscle that's essentially on the outside of your quads, and they normally take these biopsies from. Have you ever had a biopsy taken? I've had 6 from my VL. No, both of them. They're not too bad.
Yeah, no. The thought of it absolutely terrifies me. I haven't ever had a biopsy done, but I've seen it taken a couple of times, and yeah, maybe I'm just a little bit squeamish, but no, not for me.
So either way, it's done because it's a large muscle. It's in a convenient location, like you say. There's limited risk of nicking an artery or something like that, and it's also just, you can have someone sitting on a bed or in a chair, and you can just get at them from the outside. One of the other considerations is as well, it's used in most sporting events. It's a very, like, running, jumping, squatting, throwing, snatching, etc. The quadriceps are involved, they're large, and it's convenient. So that's why if you're looking at something like exercise training, typology, etc., it's a convenient muscle to get at, and it's a muscle that's probably experienced a large amount of stimulus quite regularly. So that's why it's studied. But this is a big problem in muscle fiber typology research, although maybe arguably not to some extent, which we can talk about in a while. But is that most studies, again, to keep harping on Anti-Galpin, they do have a review out from a year or two ago where they essentially assessed how many studies were done in given muscles, and I'm gonna guesstimate what it was, but I think it was something like 85+% of studies are performed in the vastus lateralis. And something listeners may not be aware of, but a given muscle will have an inherent fiber typology. So for example, some muscles, irrespective of whether you're someone who is generally fast twitch or generally slow twitch, specific muscles will have an inherent general composition. So for example, the soleus muscle in all people is generally mostly slow twitch muscle fibers. And what you would see in someone who maybe has a consistent fast twitch typology, as in they are someone who is mostly again in parenthesis, or has a high abundance of fast twitch fibers, they might have a higher relative percentage of fast twitch fibers in their soleus compared to the general population, but it still will be mostly slow twitch in that specific muscle. So it's hard to generalize kind of sometimes, because most research is done in the vastus lateralis, but again, that's mainly for practical reasons. But just an aside to comment on.
Lovely. Now, just before we get to the results, I want to talk briefly about the two techniques they use, because they use them in a way that they were, I suppose, complementary of each other, because both have inherent limitations. So there's the single fiber technique and the homogeneous composition. So I'll let you take it away on this one.
Yeah, you might, Jamie, you might pull up those images I sent you there a little while ago. Jamie, pull that up, just because I think that's a nice way. So people who are looking on YouTube, this might be something that's worth looking at. But yeah, one of the things they do here is they compare two methods of muscle fiber typology or typing, muscle fiber typing, something called a homogeneous analysis and something called a single fiber analysis. So for people who are looking at the screen, this is what a muscle biopsy sample looks like when you extract it. So they're usually, and I think in this study, if I remember rightly, samples were about 15 to 20 milligrams, which is kind of the standard amount of muscle you would take for or you would separate a muscle biopsy into. And this is essentially what the sample looks like, which is, if you're listening on audio, the way I would describe it is kind of similar to a slightly cut up wine gum sweet, the red wine gums like that, but not as perfectly circular. That's kind of what they look like. And a homogeneous analysis then is essentially where you would take one of these fractions of muscle biopsy and you would, for lack of a better word, you'd grind them up, and then you would run assays on them. And the way you fiber type is you would conjugate antibodies. So these are antibodies that are made in a lab, and they're specific for MHC proteins usually. That's the technique they've used here. There's other ways of doing it, so we'll only talk about it from that perspective. So you get your antibodies for MHC proteins, you treat them to the homogenated sample. So what happens is you've antibodies for MHC1, MHC2, MHC2A, MHC2X, and they're introduced to the mix, and when they find those proteins, they'll bind to them, okay? And what that'll do is you can then quantify them via a technique called densitometry. So there's a method called the Western blot, which is a very common method in molecular biology. You essentially can separate proteins out by their molecular weights. You can identify them and you'll get a stain. You'll produce a stain on a sheet, essentially a gel. The strength or the intensity of the stain, so how apparent a stain for specific protein is representative of how much of that protein is present in the sample. Densitometry is a technique where you essentially, a camera takes a picture of the gel and counts the pixels on the stain, and that's how you get a kind of quasi quantification. So with the homogeneous analysis, what you do is you will get an idea of the total amount of MHC protein overall that's present in the sample, and then you'll quantify the relative abundance of each of the major MHC proteins. So MHC1 for type 1 fibers, MHC2A for type 2A fibers, MHC2X for type 2X fibers. And then what you can do is, relative to the total amount of MHC protein you've detected, you can see which muscle fiber type is present in relative abundance. The, in kind of quotation marks, issue with that technique is you can only use it to detect let's say the main subpopulations of muscle fibers. So you can only detect like type 1 muscle fibers, type 2A, type 2X fibers. It will also kind of, let's say, mislabel hybrid fibers. So I might have a type 1, type 2A muscle fiber. How do I know if an antibody has bound to a type 2A fiber, or if you have a fiber that has both, you've got the antibodies binding to both, but because it's a mix, it's like a cocktail of all the muscle blended up together, you don't know if that level of detection came from the same single fiber, essentially, if that makes sense. You just know how much you've basically gone, I know how much MHC is here, and I know the relative mixes of each MHC protein, but I don't know, how many fibers it came from, which fibers were co-expressing, etc. That's how that technique works.
Cool.
The next one then, this is kind of the more cutting edge style of analysis. It's fascinating that we're able to do this type of work, is single fiber analysis. So I can only see the first image there. I don't know if that's the way you've done it, but essentially for people who are watching, so this is kind of obviously this image is, I don't know if I would say it's doctored, but it's obviously been touched up.
You can see that
it's a form
now?
of yeah, I can see that. Yeah.
Cool.
It's a form of electron microscopy where they've taken a picture of a bundle of muscle fibers here. So you can see this white stuff that's covering. So for people who are listening, essentially what you've got is, the way I would describe this is, if anyone ever ate cheese sticks as a kid, did you ever have cheese sticks, Arthur? They're nasty stuff. They're essentially just cylindrical circles of cheese, and people would split them at the ends, so it would look kind of like their mascot was like a guy with like split end hair, kind of made
pulled
of
pork
cheese,
might
obviously.
resonate with me a bit more.
Yeah, pulled pork is another good example. And so if you want to picture it as a cheese stick or pulled pork, whichever way you want, you've got this kind of sample of tissue, and you've got these kind of split ends that are all protruding from it. There's kind of a white sheath over the whole sample, which is fascia. And then you've got each individual kind of split end, which is bundles of muscle fibers. So in single muscle fiber analysis, what they'll do is they'll take a homogenate, and they'll treat it in certain different ways with specific chemicals, and you're able to essentially extract individual muscle fibers. So again, if you're watching on YouTube, you can see each one of these individual fibers would be extracted. When they're extracted, then you'll do something similar to what you would do with the homogeneous analysis, which is you will essentially introduce a cocktail of antibodies to each individual muscle fiber. And from that, then you can identify which MHC proteins are present. So for argument's sake, I put in a cocktail of MHC1 antibodies, 2A and 2X, to a single fiber. If I only get a signal for 2A, I know that there was no antibody binding to MHC1 or MHC2X. Therefore, this is a pure MHC2A fiber. Similarly, if I got a signal for MHC2A and MHC2X, well, then I know this was a hybrid fiber, because both were detected. And essentially what you do in this technique, it's a bit painstaking. You'll separate as many individual fibers as you can from an analysis. It's normally in the range of hundreds. I think in this study they extracted about 105 fibers, I think, per athlete. So from however much muscle they took, and you'll apply that technique to each individual one. So I have 100 fibers, let's say, to be easy. I've done this technique on all of them. If 20 of them were type 1, 60 of them were type 2A, and 20 of them were type 2X. That's an estimate of my fiber type distribution in that muscle. So 20% type 1, 60% type 2A, 20% type 2X, just as a rough example. That's obviously an estimate for the whole muscle, but based off the sample, that's essentially how you do it. So you painstakingly do each fiber, and then based off the number of fibers you took, the amount of identification you found, you kind of generate an estimated distribution. And that's how the single fiber analysis works.
Cool. So I'll come back to the paper then. And as always, I'll skip over the statistics and straight to the results. So obviously the standout thing here being the abundance of type 2A fibers in this sample. So 67% on average, and I think it says somewhere it's even higher when you're looking at the females only. I can't see that there. Maybe I'm raving, but I thought I saw that at some point. Anyway, interestingly as well, there seems to be something unique going on with the super heavyweights. In so far as like when you're looking at and maybe this is highlighting the limitation of the homogeneous technique, in that it detected different proportions of type 2X and type 2A, type 2X hybrids for this, I think it's 6 super heavyweights. There's an asterisk beside each of them here in the table.
Yeah. So yeah, I guess the first thing to say is, sorry, just for people who are looking. So this table, and if you want it, this paper is open access, by the way, just for that's probably something we should have mentioned earlier than 30 minutes into the podcast. But
yeah, sure.
So
we'll include it in the show notes anyway. So
this is table 3, which shows the kind of relative percentages of each muscle fiber type, comparing the 2 techniques. So yeah, what you're talking about is the type 2X, and that's one of the things I wanted to do was, how consistent are the estimations of these techniques when compared with each other. And you were mentioning the type 2X muscle fibers in the super heavyweights. So I actually can't remember what your point was there. Sorry, that was just me being very self-absorbed.
Yeah,
in my own opinion.
Who cares? I'm just spoofing. No, what I was saying was that when you look at the homogeneous analysis, you seem to get this anomaly of basically detecting type 2X fibers that aren't detected with the single fiber analysis. So I think that they've made the point that this highlights the limitation of the homogeneous composition analysis, because it's not specific enough to rule those out effectively. So that seems to be an error, or at least that's how they phrased it anyway.
Yeah, but there's 2 things to unpack there. The first is something so this is table 3 in the study for people who want to have a look at it. But the first thing to note is that it's only super heavyweights where they actually detect pure type 2X fibers at all. And that's only through the homogeneous technique, if I'm looking at this correctly.
Mm-hmm.
So what that could be is, and firstly, this is something that people who don't work in molecular biology might not realize, in that this work is very noisy in general. It is always very noisy, and it's I would always be, and I don't mean this about this paper specifically, but in general, you need to look at these kind of studies with a degree of hesitancy about major findings. But one of the things you would see, why you might see this higher proportion of type 2X in the detected in the homogeneous sample could be something to do with the fact that it might be essentially mislabeling hybrids. Because again, remember that homogeneous, you're for lack of a better word, you're sticking it in a blender. Now that's not exactly what you do, but so you're not actually analyzing intact fibers anymore. You're just looking at the relative amount of protein in a bit of mush, essentially. So what you'll find is these super heavyweights who do have the type 2X fibers identified via homogeneous analysis, and that's the only type of type 2X fiber that a homogeneous analysis could detect is let's say a discrete subpopulation. These guys also have the highest abundance of hybrid 2AX fibers as well. So these are probably hybrid fibers. Now, one of the things is it's the relative percentage is quite different for most of these. So for example, looking at participant 6, just because it's the closest to my field of vision, they have 13% type 2X fibers estimated by homogeneous analysis, and 28% type 2AX fibers estimated by single fiber analysis, and no pure type 2X fibers by single fiber analysis. So obviously that's a little over double type 2AX fibers estimated there. That could just be assay variability. It could be something to do with the way the samples are processed, could be issues with the antibodies. You wouldn't know that. And again, so what I would do there is I would only read into the general message of that finding, that for whatever reason, the super heavyweights in this sample appear to have the highest abundance of MHC type 2X expression. So the closest to a type 2X phenotype, essentially. Now, there is some stuff in there, like, for example, you'll see a higher amount of relative amount of type 2X fibers in people who are larger in general. And by larger, I mean like obese sedentary people, you know, compared to say non-obese sedentary people, you might expect to see that. So that could just be, and I think they do comment on that in the discussion. It's not clear if that's an artifact of size or if it's an artifact of, because these are super heavyweights. I think, again, they're mostly females and they're 90 kilos or above. And super heavyweight females in weightlifting can go far above 90 kilos in body weight, you know. So that's kind of where the mishmash comes in. It's not entirely sure if that's associated with their status as a weightlifter or if it's just a byproduct of the weight class they inhabit and the body composition that's required for that. So
Sure.
yeah, I'm speculating myself as well,
Yeah.
you know. But the difference could simply just be down to assay variability and you know, antibodies can bind off target as well, you know, that does happen. So you can get, now it's, you know, obviously you want antibodies that have a low probability of doing that, but it can happen where like a type 2X MHC antibody might bind to type 2A poorly, but by accident, you know, stuff like that can happen, you know, as
Sure.
well. So that could explain some of the difference.
One thing just to clarify for anyone who might be confused as to why in this table you're seeing more columns with SF, the single fiber, compared to HG, the homogenate. So as we noted earlier on, the homogeneous composition analysis isn't sensitive enough to detect these hybrid fibers, the MHC 1-2A hybrid and the 2A-2X hybrid. So that's why you're only seeing a column for single fiber analysis under each of those.
Yeah, exactamundo.
So anything else in the results that you want to comment on or that you thought was noteworthy?
No, I actually think if you just go to the figure, because I think the figure is, if I'm correct in saying, is just a rehash of the single fiber data, but it's a nice visualization of the fiber type distribution.
Oops, did not mean to do that.
Of these athletes. So for example, and they actually do something nice here with, you see there's basically they've got the let's say the 5 fiber types that they've detected. So 1, 2A, 2X, and then the 2AX hybrids and the 1, 2A hybrids. And they've also got a nice little kind of continuum on the bottom here, which would show how they range from slow to fast. And what you see is there's quite a large congregation for the 3 groups. So the 3 groups of the world-class females, the national caliber females, and the national caliber males. There was no world caliber males in the study. And what you see across these groups quite consistently is a congregation essentially at the type 2A fiber as the majority. And roughly, I'm looking at this bar chart, they're all over 60%. And they did actually do a statistical analysis looking at the distributions between groups. And there's no, so this is kind of meaningless to people who don't work in science or perform inferential statistical analysis, but essentially there was no significant difference between the distributions of each fiber type for between those categories of lifters. So all you need to know as a listener is essentially in each of these groups, the world-class females, the national class females, the national class males, the majority of their muscle fibers appear to be type 2A, and there was no difference between those groups. So all of them, there wasn't any difference in the average amount between those groups. So national caliber males didn't have a higher expression of type 2A muscle fibers than national caliber females or world-class females, or whichever way you'd like to consider that finding. So that's actually interesting in and of itself, and we might discuss that in a second. I guess the 2 points about this finding, and then the final one where they discuss, they don't actually show the correlation, but they do attempt to correlate fiber types with, I can't remember if they did it with just the total or if they did it with the relative snatch. So snatch relative to body weight or clean and jerk relative to body weight. So they discuss that correlation, which they ran, but they don't display it visually. And also for lack of a better word, the sex difference or lack of sex difference in fiber type distribution in this population, which to some extent is an interesting finding because there is commentary around sex differences in muscle fiber typology in humans. So I don't know which you'd like to dive into first.
Sorry, up to you.
Well, I guess the first thing is we kind of rehashed this in the introductory section, in that type 2A may be surprising to some people because they would say, oh, surely it's type 2X given the nature of the event. But I guess we kind of I won't labor on that point longer, but I would just say it's not unbelievable that it's mostly type 2A as the highest abundant fiber type in this population.
So just before you continue there, I'm just going to rudely interrupt you, but
that's okay.
One thought I had on that was, you might think that when you think of the actual performance of the task in competition, but when you break it down to like the training that's involved, and you think, well, a type 2A or a fiber type composition that's got a higher proportion of type 2A would be more favorable to support that type of training, if you get what I'm saying. Because when you're training for weightlifting, you don't just do 3 snatches and 3 clean and jerks and then go home and rinse and repeat a few days later. There's, to support the level of volume and the training density, I suppose, a type 2A, or again, like a higher proportion of type 2A fiber type composition would appear to be preferential for that type of training, if you get what I'm saying.
You've actually hit the nail on the head, and this was something that was circulating in the back of my mind, but I kept forgetting it as we talked through. So I'm happy you brought it up, because you're absolutely correct. And there's work. I don't know if there's work done in resistance exercise, but there is definitely a body of work done within endurance exercise athletes. So I know obviously the majority of your listenership, I presume, have, I would say probably less than an interest in endurance training. In fact, they may have a severe immunological response to endurance training and endurance training discussion. But you do see, one of the things you see endurance training coaches talk about sometimes is training athletes differently based on their fiber typology. And why I bring that in is, one of the things they say is, for example, in interval training sessions, athletes who are, in quotation marks, more type 1 in endurance training are generally posited to need shorter recovery times between intervals, or like, for example, type 2A or more type 2 focused endurance athletes, now obviously that's relative, might need longer recovery times in intervals, and they may also need to run fast intervals kind of slower because their absolute speeds might be higher, but that takes more of a toll on them. So that's one of the things, and there is a body of work in endurance training looking at that athletes, now I believe it's small, but that basically athletes with a higher type 2 muscle fiber typology do need to be mindful of their recovery slightly differently in comparison to athletes who are more type 1. And then if we want to be speculative, we can extend that to talking about fiber subtype populations. So if you're taking that kind of as a for the sake of thought experiment, for the sake of discussion, if you take that as a rule, then in theory, an athlete who is more type 2X would also have a lower ability to recover even within a training session compared to an athlete who is more type 2A. And there is some physiology behind that as well. So for example, the capacity for things like glucose uptake is higher in a type 2A fiber compared to a type 2X fiber. And what that means for recovery is, like we talk about things like glycogen. Glycogen is carbohydrate that's stored within muscle fibers. Glycogen depletion does occur with resistance training. And there's actually a nice study from a year or two ago. Maybe we could discuss that in another podcast, that looks at fiber-specific glycogen depletion in response to exhaustive resistance training. And it does occur, and it occurs a substantial amount. And that has implications. I know people are like, why do you care about like substrate utilization during resistance exercise? But actually glycogen depletion does have implications for fatigability during resistance exercise training. So carb up is one thing I should say, but also essentially it's maybe harder to get a type 2X fiber to recover from a training session than a type 2A fiber as well. So not only will it be kind of, maybe you would have to train slightly differently if you're more type 2X. And obviously, I don't think there are many humans, if any humans around, who have some kind of majority type 2X phenotype. I don't think that's a thing, particularly if they're trained. But it may just be more that, like you say, a type 2A muscle fiber is more conducive to high quality training. And high quality training is very important for high quality performance, of course. So that does actually make sense on a level as well, with what you suggested. And I would agree with you, I think.
Very good. There was another point you wanted to make as well about the results before we move on.
Jesus, which one was it? The sex difference, is that it?
Maybe that was it, yeah.
Yeah, I think those were the two things. Yeah, so, well, the sex difference one is interesting. They comment on this in the discussion. So you will hear this anecdote passed around, even from physiologists. And sometimes I hum and haw about what I believe about it, because it hasn't been exhaustively researched, particularly with regards to high quality studies. But there is, there's maybe a kind of common speculation that men tend to have more type 2 muscle fibers than women. And the reason, there's a couple of reasons for that. Obviously, firstly, type 2 muscle fibers are larger than type 1 muscle fibers. So obviously men have a higher muscle mass compared to females. And part of that is maybe due to the fact that more type 2 muscle fibers, larger muscles. There's also some kind of, there's I guess you would say, physiological evidence of why that might be possible as well, in terms of, so things like testosterone can induce type 2 muscle fibers. So there's a process called kind of fiber type switching, and it generally only occurs within, well, we're kind of, to the extent with which we're confident it occurs as a process, it occurs mostly within type 2 fiber subpopulations. Essentially, type 2X muscle fibers transition to type 2A muscle fibers with training. It's possible that type 2A fibers may transition to type 1 muscle fibers, but and that's, people do think maybe that's a thing, but the general agreement, or my understanding is, the general understanding is it's a slower process to occur, and it appears harder to capture if it does occur at all. So my point in that is that testosterone seems to be capable of inducing kind of type 2X to A muscle fiber transitions, and maybe type 2 muscle fiber phenotypes. And obviously males particularly, something that would be interesting to look at, and maybe it's been studied, is the fiber typology of males pre and post puberty. So if you take a male when he's 10 or 11 years of age, you take a muscle biopsy from him, you do typology, and then you take him when he's 18 or 19 and see how the typology has changed. Obviously there's a lot of variability there, but there maybe is, and I'm being entirely speculative here, so please don't anybody shoot me down for this, perhaps the potential for a puberty induced type 2 fiber transitioning and stuff like that. But that's generally the idea of why there is this idea that gets passed around that men have a higher proportion of type 2 muscle fibers compared to women. Obviously, in this study, there's no evidence of that whatsoever. And this is a high caliber strength trained group, and they're elite weight. They're all elite, definitely, by at least, a strict definition of elite to me. So what that would say is, if there is, say, basal differences in muscle typology between men and women, and even again, that's an if, that is not by any stretch fact, but if there is one, it seems training, a high degree of training, appears completely capable of removing that difference, if it even exists, which is a very interesting finding, particularly because they've used quite accurate techniques for typology.
Right. Lastly, then, on this paper, because we're coming up on an hour now, and it basically, so I think I mentioned this to you before we started recording, but I kind of feel like this is akin to if you studied basketball players and found, lo and behold, they're really tall. So it's kind of like, it's interesting, but it's suppose the point I'm getting at is like, what can I do with this information? Or is there anything, any kind of closing thoughts you'd have about it, or how this could be related to someone who's in their own training? Or is it a case of, look, this is what elite level performance is, and the sport sort of self-selects for the high level performers?
Yeah, now what you've done is you've opened Pandora's box there, because you've unfortunately, I'm sure anyone, the two people who've made it to the end of this podcast at this stage may realize that I'm a man who's fond of a tangent. So there's actually two things there, and there was one other kind of result I wanted to discuss, but it ties into the question you've asked me, so that's nice. That's a nice way to wrap up. So they mentioned this correlation about, and again, I don't recall if it was relative snatch, and that's the snatch amount relative to the body weight of the athlete, relative clean jerk or relative total. But in either case, they found no correlation between the, and they don't present that data visually or in a table. They just say there was no correlation. Yeah, percent snatch or clean jerk relative to 1RM when analyzed as subgroups or when combined together for, they say single fiber or homogeneous analysis. So I presume, so they're fast twitch fiber percentage. And people would look at that and go, hold on now a minute, but why would they have all these type 2 fast twitch muscle fibers and then they don't correlate with their performance? The hesitance I would put there, and the way to consider that is, this is a group that has been, it's similar to if you look at VO2 max in elite runners is not a very good predictor of race performance time. So these kind of traits are very good at discriminating between groups of performers, but not between performers within groups. So what I mean by that is, you say there's no correlation between the performance of an athlete here and fast twitch fiber type abundance, but that's because they've all got a high amount of fast twitch muscle fibers. So basically the correlation is like, if you were to imagine the correlation table, and let's just say there is a correlation between weightlifting performance and type 2 muscle fibers, they're all in the top right hand corner of the correlation, so they're all at the top. They're all in the same location on the theoretical population graph, which is why you don't see one. So what you would see is, for example, say I had a very, very low abundance of type 2 muscle fibers and I happen to be a weightlifter, and you plotted my point on the graph, and then you plotted a participant from this study, you would see a near perfect correlation because we're in different groups.
Yes.
But if you took a load of people who had similar fiber typologies to me, and we put only us in a group, you might not see a correlation, or it might be a very weak one. And that's just the nature of the group differences. So essentially they've been selected for their fast twitch muscle fibers. And now within their groups, there is other factors that contribute to, for example, technique, their performance level. So that's just to explain that finding, because it is a bit of a funny one. Now, the question that you asked me is that, how is this actionable? I actually would say, don't worry about it, because there are people out there who, they read these types of studies or hear these kind of things and they go, oh, I'm a former endurance runner. I'm in my late 20s now and I got into Olympic weightlifting. I really enjoy it. I want to pursue it as a sport. But sure, like, I'm all type 1 muscle fibers, even though I've never had a muscle biopsy. I'm all type 1 muscle fibers. I'll never be a good, like, what's the point? I think people get caught up in these physiological kind of arguments, and the point is that you enjoy it. That's to me the point. So I would say, don't worry about what you're like. If you're a competitive weight, and you'll also get people who are, say, good competitive weightlifters, but they're not like elite. They might be on kind of like, say someone, for example, someone like me who's put up, I put up a 285 total as an 85, which is decent, but it's not very good on any kind of elite level, so like someone like me could be like, oh, maybe I'll get my muscle fiber type done and I'll find out I have lower percentage than these people. I'm never going to make it, and I stop weightlifting. You're like, what's the big, like, you're better off not worrying about these things. That would be the thing I would think about. It's not actionable in the sense that like training will alter your fiber typology, particularly within your type 2 muscle fiber pool. But over, say, a decade of training. By how much, I have absolutely no idea. And I don't think anyone could say with any massive degree of confidence. This is a cross-sectional study. So these are these athletes who have been essentially plucked out of a pool and examined. They haven't been followed over any period of time. So what, say, like the starting typology of these athletes were when they started weightlifting, or they started, resistance or power training, we don't know, so we don't know how much of this is nature and how much of it is nurture. That's one thing. So I would say, yeah, look, it's not actionable. You're not going to be like, there's no specific training techniques to improve your type 2A fiber abundance or anything like that. Well, there are. It's called weightlifting or powerlifting. But, so I would just say, I hope you enjoyed listening. I hope you found this interesting, but keep on keeping on. That would be my closing statement, unfortunately.
Definitely. Yeah. And to that point, I think sometimes it's better not to know. Yeah, because it's
always better not to know.
Yeah, you can nocebo yourself. Cool. All right, that just about wraps us up, Ian. This has been a fun and longer than I expected chat. I thought this would be a 20-minute one where I'd be struggling to find stuff to elaborate on, but no, we got a good comprehensive analysis of this paper. So thank you so much for giving up your time and sharing your knowledge and your thoughts. And any closing thoughts before we say our goodbyes?
No, unfortunately for you, I'm not a man of few words. So no, thank you very much. This type of stuff really excites me. So it was great just to have an opportunity to talk about someone other than my shower wall about it. So thank you very much for having me on, and looking forward to the next one should it occur.
Love it. Take care, and we'll talk soon.
Cheers. Bye.